Welcome to a marvelous Math Monday, everyone. I'm so pleased that you've all shown up for your learning. Absolutely, it's a pleasure to work with you day by day because you show up, you're ready to pay attention. You've got the handouts from last week, so you can take some great notes in the handouts. And here we go. Last week was the hardest algebra of the course. This week, and honestly, the algebra, all those like crazy rational expressions, I'm always telling you, visualize the answer first, but I can't visualize those. I can throw them into Desmos and see what they look like, but I'm never using those visualizations for error checking and things. This topic that we're doing this week is working on parent functions and then transforming those parent functions to look like new and different functions. This is the most visual, the most imaginative work that we're going to be doing together in this course. So if you haven't been kicking on that visualization muscle yet, you absolutely want to start kicking that visualization muscle on right now. The right brain and the left brain can absolutely work together in math class, and it creates a much more enjoyable experience. You can learn to enjoy math as much as I do. So here we go. Our goal today is to identify the parent functions from their graphs and equations. So if you can do this by the end of the lesson, we are good. Okay. We're also going to be looking at the transformation form of things. This is just an introduction to the algebra we'll be looking at this week. Right now, this probably looks like a soup of letters. Someone described it this morning of like looking at their alphabet soup, and that's fair. That's a fair thing to say right now. But the visualization should be pretty clear. Okay, and because we're doing a lot of visualization in this unit, I've got a handy Desmos ready to go. I also have the Desmos app on my phone. Hands up who has the Desmos app on their phone. Yeah, a similar thing happened this morning where a few hands went up, and those hands also tended to go with students that are doing pretty well in the course. So you want to be one of those students who's doing well in the course. Put the Desmos app on your phone, and when you see a problem that you're like, I don't know how to visualize that, throw it into Desmos, and Desmos will help you visualize. Okay, let's go. So our first parent function, what's this idea of a parent function? Well, it's the simplest function in a family of functions. It's the function from which all of its variations are derived. So we have a linear family of functions, and that the basic one is just y equals x. F of x equals x, or y equals x is the parent function. Let's do a table of values for y is equal to x. You can always create tables of values when you're confused. That's another way to help your visualizations. If x is minus 2, what's y? F of x equals x. Yeah, what about negative 1? Negative 1. People see the pattern, right? So I can just continue? Yeah, x maps to y directly. So take your table of values and put it onto your graph, and you will see another pattern that by taking a ruler through these points, I can draw a straight line. It links all of those points and even includes the points in between. And points we haven't even forecasted yet on our table of values are also all there. I was showing my 7-year-old daughter this morning that with a ruler and a piece of graph paper, she could practice her times tables. If you want to look, that's the ones times table. If you want to look at the 2 times table, look at the line y equals 2x. If you want to look at the 10 times table, look at y equals 10x. And you can do your times tables on graph paper that way. You need a lot of graph paper pretty quick, though. Desmos, though, can do it. Desmos is infinite graph paper. All right. So what the heck is this transformation form that you're talking about, Mr. Jennings? Well, in this case, I'm going to teach ahead a little bit here. If you don't understand, don't worry. Okay? We can multiply inputs and outputs, and that will transform the function. Multiplying inputs and outputs is usually results in something different. Sometimes it results in the same thing. We can also add or subtract to inputs and outputs, and those will also do different things to the function. We have different letters that correspond to those things. If I want to multiply outputs, that's the A. The A is out here. It's multiplying the output of f of x. All right. If I want to multiply inputs, that's this K value in here. It's hugging the X inside. It's multiplying the inputs. If I want to add to outputs, that's the C value. It took the whole function here, f of x, and then added something. So C values add on to these functions, add on to their outputs. And if I want to add or subtract to inputs, it's in there, the x minus d. So that's the meaning of these four variables here, d, k, a, and c. They're either adding or subtracting, or multiplying and dividing, inputs or outputs. And that's their role of those four things. So if we were to write f of x in its transformation form, like I could create a new function g of x that was a transformed version of f of x that would look like this. A multiplied by bracket k multiplied by x minus d bracket bracket plus c. And I don't want to explore that one too much right now because algebraically it's not that interesting. It always reduces to some y equals mx plus b. We have four different numbers there, but they're going to wind up being mx plus b, just two, m and b. With quadratics, it's more interesting. They can make three numbers. And with some of the other functions we're going to look at, they can retain their independent nature and stay four values. So let's take a look at the next family of functions. F of x equals x squared. This family is called the quadratics, and their pictures are parabolas, and sometimes they hide treasure at the vertex. Over there. So here, let's fill in our table of values. What is 0 square to? 0. So let's put that 0, 0 on there. And then 1, it squares to? 1. What is a negative 1 square to? 1. 1. What is negative 2 square to? 4. 4. And what is 2 square to? 4. 4. Good. So put all these values, all these points on your table of values. This, my friends, is the parent function for quadratics. You're going to link it all with a beautiful curve that just slices those points right down the middle and predicts future values with some arrows there. Okay, there's our parent function. And let's take a look at the transformed one. So we might have a g of x, which is equal to, multiplying my outputs would be a, multiplied by the function f of, oh, wait, we didn't write that. No, I'm doing that wrong. Sorry. A multiplied by k, bracket, x minus d, end bracket squared, plus c. This is what it would look like if we have those four transformation values in there. And now I'm going to teach the whole week, and don't let me stay in Desmos for more than 5 minutes, okay? Here we go. So, yeah. Sure. One moment. So I'm going to prepare my parent function. It's f of x is equal to x squared, all right? And let's create a new function, g of x, that is a transformation of f of x. Okay, so if g of x just equals f of x, you'll notice these two functions are the same. But let's multiply that by some value, and then we're going to call that a. When a is 1, they're the same thing. If I multiply by a number bigger than 1, notice that it's changing the, what aspect of the parabola? It's just the stretch factor. In this case, a is just stretching all of my vertical things. If I have a as negative, then it's also a reflection in the, which axis? Reflections in the x-axis. So the x-axis is acting like a mirror here. Okay, cool. And then if, and then what would happen if we were transforming a single point? Let's check what happens when a is 2. There we go. And we're looking at the point, I'm just going to show us some points with x equals 1, this line. And this is a Desmos trick you can do if you want to find like some exact points. You can do that. Let's zoom in a little bit on this stuff. Notice that the point 1, 1 got stretched up to the point 1, 2. Cool. Because we're multiplying the output by 2, so it got stretched upwards by factor 2. See, because we're multiplying, this is a times f of x, so this is 2 times f of x there, when the slider's set there. As I change the slider to 3, it goes up to 3. It's now stretch factor 3. Okay. Notice that 0, 0 did not stretch or change, even when a is negative, because 0 multiplied by anything is still 0. So that point is like an invariant point. It does not change under that particular transformation of multiplying the outputs. And any zero won't. Okay? Let's, instead of having a there, we're not going to have the slider anymore. Let's multiply by k. And we're going to add a slider for k. So now this transformation is now multiplying inputs. Let's see what happens as k goes to 2. Wait a minute, that stretched a lot more. Stretched up to 4. Zoom out a little bit. And see what happens if I go k is up to 3. Any predictions? Oh, it's up at 9 now. Let's see if k is negative 3. Oh, wait. It didn't reflect. It went all the way down and then came back up. It went all the way down and came back up. K did not reflect when it went negative. Oh. Any algebraic ideas for why this strange thing is happening? When we multiply the input values, it gets squared. It's subject to the machinery of the function. Okay? So, if we look at a case like we have f of x is equal to x squared, and then g of x is equal to f of 2x. That's a set of instructions saying take f of x and substitute in for x 2x. So 2x gets squared, so 2x times 2x is 4x squared, is the equivalent function. So that's getting multiplied that way. When you think about a values, you can think about just adding to the stretch factor and a vertical stretch. When you're thinking about k values, I'll give you another way to think about these. So here's k is 1, and I'm going to, instead of showing you the line x is equal to 1, let's look at the lines y is equal to 4 and y is equal to 9. All right? Here is the untransformed function congruent with the initial function. Let's go k is 2. And notice what happened to this point 2, 4. It got pulled to the y-axis by factor 1/2. See it there? So k creates compression towards the y-axis. This is tomorrow's topic. We don't need to really get it today. Now, let's take a look at this point here. That was the point 3, 9. It's now at 1/2, 9. Let's take k to 3. And we'll notice this point that was at 3, 9 is now at 1, 9. It was pulled towards the y-axis by factor 1/3. So because you remember how in vertex form of a parabola, x minus h squared plus k, the h is a sign flipper. If you're multiplying, it's a divisor multiplier flipper because it's in there with the inputs. Is one way to remember it, that it's always doing something counterintuitive if you're right in there with inputs. Okay, so that's an idea about k and a. Let's do f of x plus d. Okay, I'm going to create a new slider for d. All right, and then I'm going to do plus c. Okay, so I'll do both of these at the same time. We're going to add both sliders. I'm just going to reduce the slider for d to 0 for now. Let's take a look at c. C is adding on to outputs. As I increase c, the function achieves liftoff. It just goes up. By however much I add to c, notice its stretch factor doesn't change. Its shape is the same. If c is negative, it goes down. It never reflects or anything. It just translates up and down by whatever value I put in for c. And if I add on to the outputs, it moves up. Quite intuitive, right? Like it does what you expect. If C gets bigger, it goes up. Let's see about D. When D gets bigger, oh, it goes the other way. Oh, man. It goes the other way. See? When D is positive 5, then you have x plus 5 squared. That would be this parabola, right? Y equals bracket x plus 5 and bracket squared. That's just a visual. That's just a visualization of what this function is doing if D is 5. Okay, that's vertex form of a parabola. It moves opposite of that d. So that's why we'll commonly write d as minus there. Okay, And if we have minus d, then this positive 5, now look, it's following exactly. So remember that d is a sign flipper and c is not. D moves things left to right, and C moves things up and down. Okay? That was more than 5 minutes. I'm supposed to stop. Zoe?
Sorry, I just have to go for football.
Bye. You'll check the video later, right?
Yeah.
Maybe leave me a nice comment. Yeah. Oh, that's very kind of you. Don't do it because I told you to. Okay, so now let's keep going. So that's all of these different variables that are in there. Connor? Connor used the washroom. So that's all those different variables in there and what they're up to. I'm not going to show you that for each parent function, but know that their role is the same regardless of the parent function we're looking at. A stretches vertically, K compresses horizontally, C moves things up or down without changing the shape, and D moves things left or right without changing the shape. Let's keep going. Aha, here's a new function, the absolute value function. Anyone know those little bars, their meaning? No? No, it's not a restriction. The absolute value says, just tell me the magnitude of that number. If it's negative, just tell me how negative, and that's the answer. Like -5 would be absolute value 5. Strip it of its sign, make it positive, in other words. Okay? So let's look at it, and we'll visualize it first. I'll take away all this garbage. And then we'll say f of x, this is our parent function, is equal to this bar here, x, and bar. There it is. So there's the absolute value function. Notice that it's the same. If I didn't show you this, you'd say that's y equals x, and you'd be right. But y equals x keeps going down here. This part has just been reflected in the x-axis. So that to me looks like a laser reflecting off of a mirror, or a billiard ball bouncing off of the side of a billiard ball table. Okay? So there's a few places in the world where you'll see that straight line motion with that kind of angle of incidence equals the angle of reflection type of phenomenon there. Okay? And a real world example of this is distance. Can we have negative distance, or do we talk about negative distance in this world? No. We would use east and west to distinguish, right? So this could be a story going, say, from here down to there. This could be a story about, like, maybe you start here in Wasaga Beach and you drive to Collingwood. Now your distance from Collingwood is 0. And then you keep going until you're at Meaford. So as you start from Wasaga Beach, your distance decreases to Collingwood and then starts increasing again as you pass Collingwood. So this is a common place where you'll see absolute value functions that are describing phenomenon in our world. Again, if we start transforming this, if I have an a value, some number, and that gets bigger, it just stretches. If it goes negative, it goes down there. If it was instead a k value in here, then we'll notice that that doesn't reflect in the x-axis. It just gets pulled towards the y-axis there. Okay? And that things like adding c will just make it achieve liftoff like this.
Can you show us A?
A, sure.
How are K and A that much different? Just like K.
Well, one is multiplying the input,
Yeah.
and one is multiplying the output. So if you think about that algebraically, if k is negative, then it's going to produce a negative value inside that absolute value sign. But the absolute value sign strips away the negative anyway. So k is subject to the machinery of the function, and a is not. A is just changing the output.
So like behavior-wise on the coordinate plane, is it really all that different?
It's quite different. In some cases, they're algebraically equivalent, like with lines. But even then, still not. And I'll have to show you more specific examples later. It's super interesting to me, and I don't want to let you get me on a tangent.
What if you move K right now?
See, it does this little waggle around 0. It cannot overcome this negative nature of A. A is always flipping it down.
They're like moving the exact same. K and A.
Yeah, they're going to be the same amount of motion, but the K can't create a reflection in this case, algebraically. Yeah. Connor?
So, I don't know if you said this, but why are those two lines in the formula?
Oh, those two lines, those two bars?
Yeah.
Those two bars are a new mathematical symbol that people don't know yet. That means take the absolute value of the stuff inside. It means
So,
whatever the number is, make it positive.
What if it's negative? That's my question.
So let's say, I'll show you here.
Okay.
Absolute value of negative 10 equals 10.
So you kind of just now. What if it's 10?
Still 10.
So no matter what, even if it's like negative 1,000, just go straight to 1,000.
Yep.
Yeah.
It strips the sign. That's all it does.
Oh, okay.
Yeah.
I was so,
It's saying, tell me the magnitude of that number. Tell me the
Oh.
absolute value of that number.
So my question is why?
It's distance from 0.
Yeah. But why is k squared? Why?
It's not squared in this
It's not
case.
squared, but like also.
But it's still being absolute valued.
Why? Why does it make that like triangle thing? I feel so stupid
Oh.
asking this stuff.
No, that's good. Why does it create a triangle? I'll show you the basic one.
Yeah.
Here. Because it's the same thing as y equals x over here. And then over here, it's the same thing as y equals negative x.
So it's just mirrored.
Yeah.
Oh, okay.
It took the line y equals x and reflected the bottom half of it.
Oh, okay.
All those negative values flip to positive. Otherwise, it's the same.
Okay, so yeah, now I get it. Thank
Yeah.
you.
This is really useful for drawing trees in Desmos. You can draw the triangle and then color it in. I'll show you how to color those things in later when we get to the project this week on Wednesday. Okay, let's keep going. Okay. I could play with A, K, C, and D for far too long. Let's keep going. Let's fill in our table of values. What's the absolute value of negative 2? 2. What's the absolute value of 1? Negative 1. 1, 0, 1, 2. So put those points on your graph. And then you'll see the pattern. It's the line going up that way. And then the other line goes up this way.
Oh, cool.
Yeah, so now we would say that the range, and this is a good time to talk about the range, is y's of the reals. And 0 is less than or equal to y. We can clearly see that y can be 0, but it can't be negative in this case. If I looked at a transformed version, let's say I had g of x equals the absolute value of x minus 5, well, that would look like this, where that is the line minus 5, and it would go down to minus 5 and then go back up again. The whole shape has been moved down by 5. That's Wednesday's topic. Hi, how are you doing?
How's it going?
Good. Something I can help you with?
How's it going? How's it going?
I think he watched the letters.
Yeah. You must need to do some learning. Should I let this go or should I kick him out?
Just keep going.
Okay. I will keep going against my own better judgment. So here we go. So that would be one transformed example. All the transformed examples could look like this. G of x is equal to a multiplied by the absolute value of bracket k bracket x minus d bracket bracket. Actually, we don't need that second inner bracket, but I like it anyway. Plus c. Okay? So that's where all your transformation variables will fall. There's 4 of them: adding and subtracting, multiplying, dividing, inputs and outputs. Okay, let's take a look at another one. I'll let you copy down that transformation form, and then we keep going. Oh, no, wait, okay, there you go. You just came for Bueno? You didn't come for the mellifluous math tones of Mr. Jennings. You came for Raph's Bueno. Okay, let's keep going. Square root function. Hey, that's starting to look an awful lot like a food fight. You can wait till the end of the lesson and then walk it over. Okay, so the square root function. The square root function, what's the square root of 0? 0. Put that point on the graph. What's the square root of 1? Also put that point on the graph. Oh, we're jumping some things in our x values. That's interesting. What's the square root of 4? 2. Yeah, there we go. Square root of 9. 3. Square root of 16. 4. Put these values on your graph and graph it.
It's a sideways parabola.
Is half of a sideways parabola. We took a parabola, cut off one of its arms, and put it on its side. So that's what this is. It's exactly what it is. Yeah. And we can do domain and range statements for this as well. Can x be less than 0? When you go to university, yes, because then you'll learn about complex numbers. We don't teach complex numbers at high school. Yeah. I, that's right. Yeah. And y, it looks like y is never less than 0 either. So we would say y is of the reals, and 0 is less than or equal to y. That's the range. The domain is the same. X is of the reals, and 0 is less than or equal to x. There, done. So what are the transformations of this look like? Well, we could create a new function, g of x, from this parent function by either multiplying the whole square root. Why didn't I use an equals sign? That's so strange. I usually would put an equals sign there. Equals, I could multiply the whole output. I could multiply the input here. I can even subtract things from the input, or I can add to the output. So those are all my different transformations that I can do there. Okay, I'm going to freeze the screen there while you copy that down and prepare the visualization in Desmos for you.
Wait, how much?
6 for 1 is up for 2.
Wow. Wow, thank you very much.
Can I come sit with you?
Oh, no.
Hey guys.
Okay, let's go. So here is the.
Hey Brad.
Here are the different transformation values, and this is what happens. All right, oops, let's go. Yes, we want this, so here we go. All right, so to do the square root, you're going to have to open up this menu on your phone or on your computer and click that in. And once you do, make sure that what you want underneath the square root sign is underneath the square root sign, not inside, because inside will change things. Notice that the C has to be outside, and the A is multiplying the whole machinery. As A changes, it can reflect, and it can stretch towards the axis there. See? When K, and this will show K very clearly, watch this. K is also stretching it that way, but again, I encourage you to think of the y-axis pulling. Instead of it being increased in y, the y-axis is pulling all those x values. And watch what happens as K goes negative. Look where it went, folks. Actually, K can produce reflections in the y-axis. See there where K has produced a reflection in the y-axis. That's why we weren't seeing it with absolute value or square root, because it was just turning around. And the two arms were replacing each other. But we see it here. Okay? D is again moving it side to side, and C is moving it up and down. Okay, you want to see it again? Whee! Well, make your own Desmos visualizations. There you go. Yes, I could watch, and we could do this too. Whee! Here it comes. Whee! You want to see D again? Here we go. Oh, it's gonna slide all over the place. Whoa!
Is D like the X?
Sorry? D is the amount that things have been shifted left and right. So it's not directly, we're not directly reading x-intercept here, but it would move an x-intercept exactly that much.
So A is stretching the y values and making the x values smaller. What's K doing?
Compressing x values towards the y-axis.
That's the exact same thing.
But what if you
Feels that way, but it's different for different
Wait,
functions.
so A is stretching the y values, which is in turn compressing the x values. But K is just doing that first.
would it be considered the vertex?
We'll have to take a look at some cooler examples.
That's insane.
Like would D and C be considered the vertex?
I love the questions I'm getting, and I'm so glad we have a whole week for them. Let's keep going. So now the last new funky function that we have to cover today is the rational or the reciprocal function. The other functions here, you can look at one variation of the exponential function if you want. G of x is equal to 2. raised to the power x. You can explore this one if you want to get a preview of Unit 3 when we're going to be working on exponential functions. And then those of you on a preview of Unit 5 and a little bit Unit 4, you can look at f of x is equal to sine x and f of x is equal to cosine of x. But we're not going to do those in the lesson today.
We're graphing the things.
This is the last one. So, the reciprocal function. It's super cool. Let's take a look at it. Boop, 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 boop. Okay, let's write it. F of x is equal to 1 over x. Basically, this says whatever you put as an input, throw it on the bottom of a fraction for me, please. And have 1 on top of the fraction. So let's take a look at some values. 1, well, no surprise. If I put 1 on the bottom of a fraction, it's just 1, right? So that's why we have the point 1, 1 there. And negative 1, if I put negative 1 on the bottom of a fraction, there it is down there. Negative 1. Okay? But as x gets close to 0, or let's say as x gets big first, if x is 2 and I put that on the bottom of a fraction, I get 1/2. See there? 2 1/2. If x is 3, I'll get a third, and you'll get your favorite like repeating 3's there. 3.3 repeating, etc., right? And then over here, 4 would be a quarter, so there's 0.25, and 5 will be a fifth, there's 0.2, and then 10 would be a tenth, there's 0.1, okay? Just says throw that number to the bottom of a fraction, please. And that's the reciprocal function. If I graph a y equals x, you'll notice it's the same at 2 points, and then it's different at all the other points. It's like take this value here and put it at the bottom of a fraction. Boop, there you go. Otherwise, it's the same. All right? So let's fill in our table of values, and we'll review the algebra of dividing by fractions. If I put minus 2 on the bottom of a fraction, what fraction do I get? Yeah, negative 1/2. I float this negative up to the top of all my fractions. Okay, negative 1 just gave us negative 1. What about negative 1/2 on the bottom of a fraction? Like if I have f of x is equal to 1 over x, and then I ask you to find f at negative 1 over 2, well, you would just substitute negative 1 over 2 into this formula, right? Bracket negative 1 over 2. How do you resolve that and simplify it? No. You just flip and multiply. And don't, if the negative is tripping you up, just see that there's one negative sign there, and one negative, that's odd, so the answer will be negative. And then you do 1 over 2 on the bottom, but I flip and multiply, so it's now 2 over 1. This is 2, but negative, so negative 2. This is negative 2. How about this one? What will it produce? 1 divided by negative a quarter. Negative 4. Good. You just take the bottom and flip it to the top. It's just flip the fraction every time. It's just flip the fraction. Flip your input into its reciprocal. That's all. 0. What? You can't be 0. Why not, Caden? That makes me so happy. This is undefined, yeah. So the function can never be equal to 0. Y is never equal to 0. And x is never equal to 0 with this function. You can never have this function output something 0 because something over something is always non-zero. There's always a 1 on top. Even as x gets super big, it's very, very close to 0, but not 0. If you did, then you have to get yourself a new math teacher. Get out of class right now, you troublemakers. Dividing by 0 in my class and insisting on it. Okay, so let's put these values. So this is 4, this is 2, this is 1, and this is 1/2. Okay, you just flip those numbers, flip them into their reciprocals, that's all. And so let's graph it. 1, 1 was in there, 1, 1 was in there, 1/2 gave us 2, 1/4 gave us 4, 2 gave us 1/2, 4 gave us 1/4, and this is a line that gets very close to the x-axis but never touches it, and then starts growing extremely fast as we pass 1. And it goes off to infinity in that direction and infinity in that direction. And it has a negative component as well that hugs the x-axis from the other side. And then hugs the y-axis from the other side. Like that. So that's that function. its transformed function looks like this. G of x is equal to a multiplied by, let's put the fraction here, 1 over k times x minus d plus c. And for those of you that like to simplify your algebra, yes, g of x could also be equal to a over k times x minus d plus c. Draw a clearer a, Mr. Jennings. Sure, don't mind if I do. Why are you drawing that on a slant, Mr. Jennings? Old habits die hard. Sorry. There you have it. So these are our parent functions. Now let me take you on a tour of the type of questions that you'll want to be able to answer today. I'll come back to this page if you're still copying. So all of the questions are in your sheets here. So you can skip over that or do it if you want. Here I want you to be able to name the parent function. Some people were graphing these based on transformations already, and I think that's great. Just know you're reaching ahead. Okay. You want to be able to say, oh, there's an x squared there. That must be a quadratic. Its parent must be y equals x squared. Okay. Oh, this one is a line, and et cetera, et cetera. Okay. Draw the basic graph for the parent function. So these ones are absolute value functions. So you might have a quick sketch that looks like doing this with my mouse, not even my board. There, that's the absolute value function. H of x, done. I'm doing the homework for you. There's a square root, draw that one. There's a parabola, draw that one. With these ones, give an example of these equations. Here are different examples of equations of transformed functions that would be inside those families. Give a new example of an equation, and then give me also, I want you to do this for your own learning, some real world examples. Okay? Find me some real world examples there. Either examples that have that shape. In the morning, and you can't use this one, but it's super cool. They said the absolute value function looked like Harry Potter chasing the snitch. And he flies down, catches it in his mouth, and then flies along the ground. He never touches the ground. He's never perfectly vertically flying down, but he follows a reciprocal function. So give me some real world examples. Either it could be the shape or it could be represented by that. Like how long a relationship lasts versus how many cuddles are in that relationship. More cuddling, longer relationship lasting. So wait, that would be a linear relationship. Number of fights versus number of cuddles tends to be a reciprocal relationship. These types of things. And then name these parent functions. Da, 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 da. That's it for today. Any questions, hit me up by email, teamlearn@home. Bye.